Now let's take a look at another cycle. This is the Otto cycle. The Otto cycle is the typical gasoline engine cycle, and it's you have an example of the cycle that's located in the reference manual. Our example here, example 12, we're still on page 22. We've got air as the working fluid for an Otto cycle. We want to assume ideal gas relationships, constant specific heats, and a compression ratio of V1 over V2 equal to 10. Now, I've sketched in the Otto cycle here in the four parts of the Otto cycle, the four processes. The Otto cycle consists of isentropic compression from point 1 to point 2. Then it has a constant volume expansion from 2 to 3. Then a constant entropy or isentropic expansion from 3 to 4. And then constant volume pressure reduction from 4 back to 1. So you've got compression, heat addition, 3 to 4 is the work stroke, and 4 back to 1 is the constant volume returning to the initial conditions on the cycle. Okay, so the Otto cycle then has 2 isentropic processes and 2 constant volume processes. What we'd like to do now is determine the cycle efficiency, and then using the ideal gas and specific heat relationships, we want to find temperature T2 after the isentropic compression, and then we'd also like to determine how much heat is added from state 2 to state 3 if state 3 is at a temperature of 827 degrees centigrade. So these are some very typical types of questions and problems that you might have to work on an Otto cycle where air or you've got some other ideal gas is the working fluid. So let's go through now and do the analysis and determine what the solution is for this particular problem for the first of all cycle efficiency. And if you go to page 47 on the reference manual, you see the Otto cycle is given there where the efficiency is equal to 1 minus R to the 1 minus K power, and R is the ratio of V1 over V2, which in our case is given as 10. K is 1.4. It's found on page 52 of our reference manual under air for an ideal gas, and K of course is the ratio of specific heat at constant pressure to the specific heat at constant volume. And so finding the efficiency of the Otto cycle is very straightforward. Efficiency is 1 minus R, which is 10, raised to the 1 minus 1.4 power, and so you have 1 minus 10 over minus 0.4, which is 0.6. So it's a direct calculation of the efficiency of the Otto cycle. And of course this is a theoretical efficiency. Real engines aren't that efficient, but this would be the theoretical air cycle efficiency for the engine before any losses and without having to worry about combustion problems, anything else. Okay, B part. Find T2 for the isentropic compression from state 1 to state 2. We'll go back to the isentropic expressions that we had on page 43. It says T1 V1 to the K minus 1 power is equal to T2 V2 to the K minus 1 power. And so these become the most convenient to use because volumes are given, and we've given the volume ratio V1 to V2 is 10. And so of the various isentropic expressions relating to temperature, pressure, and volume, this is the most convenient to use when analyzing the Otto cycle. So T2 over T1 then is equal to V1 over V2 to the K minus 1 power. So that's 10 to the 1.4 minus 1, or 10 to the 0.4 power, and so T2 over T1 then is 2.51, and T2 is equal to then, converting again to Kelvin, 273 plus 27 times 2.51, and we have T2 is 753.6 Kelvin, or we have T2 is equal to 481 centigrade. So the entering temperature at the end of the isentropic compression then is 481 degrees centigrade. Now, This is not typical of all problems, but in this particular problem, in order to find the heat added in the process from 2 to 3, which is the C part of the question, find the Q added, kilojoules per kilogram, if we've got T3 of 827, you do have to use the temperature T2 that you've just calculated in order to find this. But I'll tell you what normally is done in a problem like this as soon as we get through solving the problem. Okay, we go through an analysis here of the first law. Again, plugging in the first law, Q minus W is equal to delta U. And so you want to do that on all the cycle problems. In this particular case, this is a constant volume heat addition. So volume's constant from 2 to 3, therefore there's no work done from 2 to 3. So the work is 0, and Q just is equal to delta U, which is C sub V times delta T. We're given temperature of 827. We're given a temperature, we just solved for a temperature of 481. You look up C sub V for air, it's 0.718 kilojoules per kilogram Kelvin on page 52. So Q then is 0.718 times 827 minus 481, which is 248 kilojoules per kilogram. Now, whenever you're solving problems like this on the exam, in order to avoid conflicts or avoid answers where you've got to use the answer to the previous problem in order to solve this, what typically is done is the temperatures would be given to you, and then you would just ask to be able to determine Q. And the idea is to see if you know that the heat transfer is a function of the change in internal energy, which is C sub V delta T. So not trying in this case to determine two concepts, that is how you use isentropic expressions to calculate the temperature at 2, give you the temperature 2, give you the temperature 3, and then determine what Q is from the first law considerations. And that's so you go through and determine that W is equal to 0 since it's a constant volume process, therefore first law reduces to Q is equal to delta U, and so that's equal to C sub V times T2 minus T1. So to avoid the problem of having to use an answer from a previous question in order to compute and determine the answer to C, very likely both of those temperatures would be given. And so from there you would just go through and calculate the change in internal energy. Okay, the next cycle that we want to look at is the refrigeration cycle. And the refrigeration cycle is known as the reverse Rankine cycle. And here we're going to get into the use of refrigerants, because the reverse Rankine cycle, and we're on page 24 now, is going to involve the use of refrigerants. Now, the only refrigerant that you have data on in your reference manual is refrigerant 134A. NCEES is trying to be environmentally conscious, and so we're using the new refrigerants rather than the R11 or R12 or some of the less environmental friendly refrigerants. And so when you go through the Rankine cycle here, or the reverse Rankine cycle for the refrigeration cycle, we'll be using a R134A as our refrigerant. So let's go ahead and I've sketched in for a refrigeration cycle here, I've sketched in all the relevant points for just a simple cycle. Of course, you've got the compressor that's driven by a motor, so it's a work input device into the compressor. State 1 to state 2 is typically assumed as an isentropic compression. The refrigerant leaves the compressor and enters the condenser, where it is condensed to a liquid, and the condenser operation is from 2 to 3. The refrigerant now is either a liquid or a saturated liquid, or it's in real life generally somewhat subcooled. However, for our simple refrigeration cycle that we're going to use, we're going to assume it leaves the condenser at saturated liquid conditions. Then it enters some sort of expansion valve. Expansion valve could be a capillary device, it could be a short tube orifice, it could be a longer tube orifice, but typically it's a device that expands the refrigerant from a high pressure liquid condition down to a low pressure mixture of refrigerant and vapor. And then it enters the evaporator from where, if you're in a cooling mode, this is where all your useful cooling takes place, in the evaporator or the indoor coil, if it's your household air conditioner. And then from 4 to 1 is where the cooling takes place. So 1 to 2 is isentropic compression. 2 to 3 is a constant pressure cooling in the condenser. 3 to 4 is an expansion through some sort of throttling device or expansion valve, and that's constant enthalpy. And then 4 to 1 is constant pressure evaporation in the evaporator. So TS diagram looks something like this. Is the 1 to 2 is the compression in the compressor. 2 to 3 is constant pressure cooling in the condenser down to a saturated liquid condition. 3 to 4 is constant enthalpy through the throttling valve, and 4 back to 1 is the evaporation. Now, sometimes it's useful to show these things on a pH diagram, so I've just sketched in a pH diagram for the cycle. And one of the reasons for using the pH diagram and showing it here is that what you have in R134A in your text is a pH diagram. So I'll just go ahead and put this up here. If we can zoom out, I think that will work fine just to show that. This is a direct page out of your text on page 50. It's the HFC 134A refrigerant. This is the pH diagram, and so we'll go through a kind of a sample problem using the pH diagram here, and you can see how the analysis will take place. But you don't have this in your, you don't have the pH diagram in your notes, because we're just assuming you've got the reference manual to be using here. Okay, so the typical cycle on the pH diagram looks something like this. 1 to 2 is the isentropic compression. 2 to 3 is constant pressure. State 2 is determined by the outside temperature of the condenser, which then controls the pressure, so it's a constant pressure process in the condenser, and then constant enthalpy 3 to 4 in the throttling process, and 4 back to 1 is the evaporation. So this is the type of cycle that we use for analysis. It's a very simple cycle, and we don't assume that there are any losses, and so what we're doing is just going through an ideal cycle analysis. So let's take an example now of how you do an analysis for a refrigerant cycle. Here's our cycle. We've got a refrigerant cycle that operates between 0.2 of a megapascal and 1 megapascal. We're going to assume that the refrigerant is our environmentally friendly R134A. It leaves the condenser at saturated liquid, and it enters the compressor as saturated vapor. Now, you could get some variations of this. You could end up with a cycle that would leave the condenser slightly subcooled, or it could be a situation where you'd enter the compressor as slightly superheated vapor. But the point is, you're going to be looking up all of these properties on the chart that's given for R134A. So whether it's a little easier if it leaves under saturated conditions, because it's a little easier to locate the point. It's kind of difficult to read off these values off a pH diagram. There's so many of these things that are so close together. It's very difficult to read them accurately. But whether they leave saturated or leave slightly superheated or slightly subcooled, leaving the condenser, it's just a matter of trying to get the best numbers that you can off of the pH diagram. So coming back to example 13 again, what we'd like to do is do a complete cycle analysis on this problem, and what we'd like to do is calculate the evaporator cooling, kilojoules per kilogram. We'd like to determine how much heat is rejected in the condenser, also in kilojoules per kilogram. We'd like to do compressor work, kilojoules per kilogram, and we'd like to determine the coefficient of performance for heating and the coefficient of performance for cooling. So in order to do this analysis now, we went through the theoretical analysis for a Carnot refrigeration, but this is going to be a real cycle now. So when we go through a real cycle using refrigerants, then we've got to determine the enthalpies around the cycle. And I've got a little note here: read the pH diagram as accurately as you can. This is probably these pH diagrams are probably as difficult to read as any type of figure that you can that you'll run into. And so just do the best in going around the cycle and doing the analysis. I'm just going ahead and again, we just showed the overall pH diagram. I don't think that there's a need to try and show that back up on the screen again, because it's very difficult to read. I'll just give you my numbers that I got in going through this cycle analysis, and leave it up to you when you do your review for this, that you look up the properties at the same locations I've got, and see if you agree with me that these are the right numbers that I picked off of the diagram. Okay, so if we go first of all, enthalpy at 1, this is the location of the entering into the compressor, and so I got a value of H. Excuse me, a little time here for sneeze. H1 is 394 kilojoules per kilogram, found from saturated vapor condition at 0.2 of a megapascal. H2, which is the condition leaving the compressor, which is the same thing as entering the condenser. I read a value of 427 kilojoules per kilogram, and that would be a pressure of 1 megapascal and constant entropy. And this is one of the most difficult ones to try and locate, because you're going up a constant entropy line, which is kind of curved in between entropy lines, and trying to do an interpolation of where that 1 megapascal is at constant entropy. H3 is fairly easy to locate. 258 kilojoules per kilogram is located on the saturated liquid line at 1 megapascal pressure, and so that one is fairly easy to find. And then, since the process from 3 to 4 is expansion through the expansion valve or capillary tube, then H3 is equal to H4, so it's also 258 kilojoules per kilogram. So the analysis of a real cycle, even the simple cycle that we're talking about here, is fairly straightforward once you get the enthalpies, but trying to get the enthalpies off of the pH diagrams is kind of a challenge. Okay, cooling in the evaporator. Let's just go through and make sure that understand where we're talking about here for the cooling. The cooling now is, in the case of an air conditioning system, is the cooling that is the amount of energy that's removed from let's say the house or the apartment in the evaporator coil. So that's equal to H1 minus H4. And so the enthalpies that we got for H1, 394 minus 258, our Q in the evaporator in this case is 136 kilojoules per kilogram. That's the cooling in the evaporator. Okay, so as we complete our cycle analysis and we go around this thing, we want to do the heat reject in the condenser. We want to find the compressor work, coefficient of performance for cooling, and the coefficient of performance for heating. So, heat reject in the condenser is going to be H2 minus H3, and so Q in the condenser is 427 minus 258, which is 169 kilojoules per kilogram. Compressor work is H2 minus H1. 427 is H2, 394 is H3, and so H2 minus H1 is 427 minus 394, or 33 kilojoules per kilogram. Now, notice that I didn't put in here the sign convention on this in the case of heat rejected or the work or whatever. The reason for doing this is that if you're asked, for instance, what the heat rejected is in the condenser, since it is heat rejected and it's given as heat rejected, then I just use that as a positive term. It's 169 kilojoules per kilogram, for instance, is the heat rejection. If you were asked to determine, let's say, the heat transfer in the condenser, you'd have to have a sign on that. It'd be positive or negative because it wasn't given specifically as heat rejected. But in this case, it's heat rejected, so the heat rejected is given as just a positive term because it's the magnitude of the heat rejected in the problem. Same way with compressor work. Compressor work we found is 33 kilojoules per kilogram. That is the amount of work that's required as a work input into the system, and so because it is compressor work, I kept it as positive. If we're just determining what the work was, then we'd have a negative 33 kilojoules per kilogram on that because it's a work input into the system. Okay, COP for cooling. Define it as the Q in the evaporator divided by the work of the compressor. And so evaporator, we got a while ago, cooling of 136, work of compressor is 33, so you end up with a COP for cooling of about 4.1. And then COP for heating is the heat transfer in the condenser divided by the work of the compressor, and so that's 169 over 133, which is 5.1. Now, I'll give you a little hint here in working these problems. We know that the COP for heating is higher than the COP for cooling, and the difference is the amount of the compressor work. When you're working these problems, what you should find out, or as a check, is to the accuracy of reading the tables and reading that figure, is that the heat rejected in the condenser should equal to the compressor work plus the heat rejected in the evaporator. So if you get a number of, see, the Q in the evaporator was 136, we got compressor work was 133, was 33, so 136 and 33 is 169, and that should equal the heat transfer in the condenser. So this is another check on you to make sure that you're reading the values right off the table. If you end up with a difference in the condenser work, the condenser heat transfer to be not equal to the turbine or the compressor work plus the evaporator heat transfer, then you've got a little small error in working out the answers. Also, you should have a situation here in the calculations where COP for heating is always higher than the COP for cooling, and the difference is the compressor work. Therefore, since we're dividing by the compressor work, COP for heating should always be 1 more than the COP for cooling. So if the COP for cooling is 4.1, the COP for heating is going to be 5.1. As you're working through the numbers, if you don't get these things to be roughly one difference, if you don't get the COP for heating to be roughly 1 more than the COP for cooling, it should be exactly 1 more, but if you don't get it pretty close to that, then there's probably some small error in the reading of the values off of the chart, and that's very, very easy to do. But this is just to check on you. COP for heating should be 1 more than the COP for cooling, and then when you're adding up all these things around the cycle, you add the evaporative Q in the evaporator to the work of the compressor, and that should equal to the heat rejected in the condenser. So it's just a helpful hint when you're working through the problems, just to make sure that you're reading them right. All right, the next thing we want to do is talk about psychometric relations. And psychometric relations are, and psychometric charts are important to you in working through problems associated with air conditioning problems. They are if you've not had anything on psychometrics before, this may be a kind of a completely new area to you. And so what I'm going to do is go through just for a few minutes on the psychometric chart and what's on the psychometric chart and how you would use it. I have one simple problem, it's just a lookup problem on the psychometric chart, just to get you familiar with the psych chart and how it's used. And then we will work out a problem in detail using partial pressures, and then working with the psychometric chart so you can get an idea of how the psychometric chart's built up and how you solve problems that involve partial pressures as well as the psych charts. First of all, a psychometric chart that I've got sketched here, and then I've got the copy of the one that's out of our textbook. But before we get into the much more complicated one on the supplied reference manual, what I'd like to do is just kind of acquaint you with what's on it. The psychometric chart is set up in terms of dry bulb temperature, and dry bulb temperature, of course, is just the ordinary temperature that you have outside or inside the room. So it's a hot day, it's 95 degrees outside, the weatherman always reports dry bulb temperature. Along this axis is the humidity ratio that is either given sometimes in terms of, in the case of the English units, it's usually grains of moisture per pound of dry air. In the case of the metric system, it's in grams of moisture per kilogram of dry air. Lines of constant relative humidity are running in this direction here. Lines of constant relative humidity are plotted on the chart. Wet bulb temperature is plotted in lines of constant wet bulb temperature that run approximately like this, and the wet bulb temperature corresponds pretty much to the saturation temperature of the air. And then horizontal lines, which I haven't drawn, but I'll go ahead and draw them up here and try to draw them out of the way here so that they don't really create too much interference with everything else. Horizontal lines are lines that are dew point, lines of constant dew point temperature. And the dew point temperature is the temperature at which condensation starts to occur. And then you also have, along this axis, you also have lines of constant enthalpy. Now, a psychometric chart is a chart involving mixtures of air and water. It is put together with the idea that if you're dealing in heating, ventilating, air conditioning areas, you're having to all the time deal with mixtures of water vapor contained in the air, and it is sometimes useful to rather than have to work with partial pressures, which is what you'd have to work with the partial pressure of the water vapor in the air and the partial pressure of the dry air within the air. Going through those equations is a mess every time you want to try and determine how much moisture is in the air and how much what the humidity is. There are equations that you can use to calculate this, and we're going to use those, but you'll find that the psych chart is much easier to use under some of these conditions. But the psychometric chart is only good if you're working under atmospheric pressure conditions. The psychometric chart doesn't apply if you're working under conditions where you have increased pressure over atmospheric pressure. Then you have to go into the partial pressure equations in order to solve it. So I've got an example or a copy of the psychometric chart that copied out of our book, Supplied Reference Manual, and awfully busy, awful lot of lines on the psychometric chart. But again, the little sketch that I gave you before, dry bulb temperature going along this axis down here, dry bulb temperature here. Along this axis you have grams of moisture per kilogram of dry air. Constant relative humidity lines run in these directions here. All these curved lines are lines of constant relative humidity. these lines here are the wet bulb lines of constant wet bulb temperature, and then horizontal lines would correspond to dew point temperatures. And so what we're going to do is first thing we'll do is just work a very simple problem that's just a direct lookup problem, just to look up some values on the psychometric chart. And then after that, we'll go through and work a problem or two where we have to use psych charts and also use commercial pressures. Okay, example 14, we're now on page 27. We've got just a lookup problem on using the psych charts. So we've got an air-conditioned room, typically maintained at about 23 degrees centigrade and roughly 50% relative humidity. That's not all rooms. This room that we're in right now, trying to tape this, we just found out at our break a few minutes ago that it was set at about 55 degrees, and so we were freezing in here. We now have it set at a little more appropriate temperature level, so things are a little more comfortable right now than they were earlier. But typically you maintain rooms at around 23 degrees centigrade and 50% relative humidity. So what we'd like to do on this particular problem is, this is just a direct lookup. We'd like to determine the wet bulb temperature of the space. We'd like to determine the dew point temperature of the space, and we'd like to determine the grams of moisture per kilogram of dry air. And so these are direct lookups on the psychometric chart, and so I'm going to put the psychometric chart back on here, and we'll see if we can get these things illustrated as to the points that we're on. It certainly will not be clear to you, but you can see at least the processes that we're going to go through in order to find it. Okay, so we started out with 23 degrees centigrade and 50% relative humidity. So you find 23 degrees centigrade under dry bulb temperature, so that's 20, 21, 22, 23. So you come up here, you come up to 50% relative humidity, and so 50% relative humidity intersects with the 50% RH line along here. So this great big dot, I've got several of these on here, and it's very hard to go vertically. You want to look on your own chart, and you might want to use a pencil and a straight edge and make sure that you go up and follow the line. So we're at 50% RH, and we are at 23 degrees dry bulb temperature. And so what we're asked for is, first of all, is to find the wet bulb temperature. And so the wet bulb temperature is going along these lines here of constant wet bulb temperature, means we're going along in this direction here. And so you are at about, I read a temperature of about 16.3. So if you're going along here, you're at this location here, so you're at about 16.3 wet bulb temperature. If you want to find the dew point is found from a horizontal line from your point over to the axis here, intercepting horizontally what the dew point is, and I read that as about 11.8. You can see where you are with about 11.8, but this is 10 here, this is 15, this is 11, so this is about 11.8. So T dew point is a horizontal line over at about 11.8 degrees centigrade, wet bulb at about 16.3 degrees centigrade. And now the other thing that we want to find is the grains of moisture per kilogram, grams of moisture per kilogram of dry air. And so we move over to this axis over here to locate that, and I didn't draw a very straight line to get over to it, but it's about 9 grams of moisture per kilogram of dry air. And so a psychometric chart can give you a lot of information very, very quickly for atmospheric pressure conditions, where you're looking at for the property, how much moisture is in the air, what temperature it's going to take to cool the air down in order to, like in the dew point, that's the temperature you've got to cool it down to in order to have moisture removal. And so the psychometric chart is a way that you can get some fairly good answers for heating, for cooling, for humidity, for RH, and that sort of thing. And so, the reason for putting this one example in to start with was just to kind of acquaint you with the psychometric chart, how it's used, what variables are on it, what information you can find from it. What I'd like to do next is to use some of the psychometric relations and the air-water relations for mixtures to determine partial pressures. And this is going to be one of them that this will get kind of long and involved, but what we want to do is look at partial pressures and psychometric relations together to see how these things kind of fit together. We've got this example, we've got 100 cubic meters of an air-water mixture. So the volume is 100 cubic meters. We've got an air-water mixture. We are roughly at atmospheric conditions. And so we've got a pressure of 100 kilopascals, which is roughly atmospheric pressure, 35 degrees C, and 70% relative humidity. This is a condition that could very well exist in the state of Texas in the summertime with very high temperatures and very high humidities, and very miserable if you're outside in this kind of weather. We want to find 4 different things out of this. We want to find the humidity ratio, which is defined as omega. We'd like to find the dew point. We'd like to find the mass of the water vapor, and we'd like to find the mass of the dry air that's contained in this 100 cubic meter volume. Now, we're going to do this 2 approaches. One is we're going to use the partial pressure equations and the steam tables, which is using Dalton's law of partial pressures and the information out of the steam tables, because the water vapor existing in the air is really steam, except it's at very low pressure conditions. And then we also want to use the psychometric chart and the psychometric relations to solve the problem. In many cases, as long as we're talking about atmospheric pressure, you can get a lot of the information and solve it much faster off the psychometric charts than you can using partial pressure data. However, if you don't have atmospheric pressure conditions, if you're not very close to atmospheric pressure, you can't use the psych chart, and you'd be forced to go in and use the partial pressures and the steam tables in order to solve the problem. Okay, so we're going after the four things here: humidity ratio, W, the dew point, the mass of water vapor, and the mass of dry air. Okay, relative humidity, first of all, defined on page 45 in the reference manual. Relative humidity phi is defined as the mass of vapor over the mass of the vapor at saturation, m sub v over m sub g. Relative humidity is 100% if the air is fully saturated and you can't get any more water into it, any more vapor into it. So, and relative humidity would be very low if for small amounts of water vapor compared to what could be contained in the air at that particular pressure condition. So phi, which is relative humidity, is defined as either m sub v divided by m sub g, or pv over pg. mv is the actual mass of the water vapor, mg is the mass of the vapor at saturation conditions for the pressure, pv is the pressure of the vapor, p sub g is the pressure of vapor at the saturation temperature. Okay, so in order to solve this problem by means of partial pressures, we've got to say, all right, now we've got water vapor in the atmosphere. It's going to exist as essentially as low pressure steam, and so we can go to the steam tables, page 48. Steam tables, page 48, at 35 degrees C, and we can find at 35 degrees C what the saturation pressure of the water vapor is in the atmosphere. And so if we were to go, and I'm going to pull back my steam tables here for just a second. This one table on the steam, from the steam tables, we're in the saturated water condition, and let's see if we can pull this up here. Okay, 35 degrees C is where we are, and 35 degrees C says that if we are fully saturated at 35 degrees C, we've got a pressure of 5.628 kilopascals. That's the saturation pressure corresponding to 35 degrees centigrade. So 5.628 kilopascals is our saturation pressure corresponding to a temperature of 35 degrees. And so if we put this back on, let's see, get us back in here. Yeah, steam tables, page 48, 35 degrees C. PG is 5.628 kilopascals. That's what we just came up with. Okay, now, using the expression that the relative humidity phi is equal to PV over PG, we can actually solve then for the partial pressure of the water vapor in the atmosphere for this particular condition. So we're given that we've got 70% RH to start with. We just found PG was 5.628 kilopascals, and so we can then find PV, which is the partial pressure of the water vapor. Okay, so PV then is equal to 0.70 times 5.628, which is 3.94 kilopascals. So this represents the partial pressure of the water vapor in the atmosphere for this particular mixture. We're given that the overall pressure is 100 kilopascals, and so the overall pressure then is made up of the pressure of the dry air and the pressure of the water vapor. So if the pressure of the air is 100 kilopascals, we've got the pressure of the vapor in the air is 3.94 kilopascals, then the pressure of the dry air in this mixture, the dry air, has a pressure of 96.06 kilopascals. And so this gives us then, on the partial pressure basis, we've got a partial pressure of 96 kilopascals for the dry air and about 4 kilopascals for the water vapor. Okay, humidity ratio then, defined by equation in your text. Humidity ratio omega is equal to 0.622 PV over PA, which is 0.622 times 3.94 over 96.06, and so omega comes out to be about 0.0255, which is defined as the mass of the vapor divided by the mass of the air. That's the humidity ratio, the mass of vapor to the mass of the air. Okay, so that's all of that is required looking up on the steam tables to the calculation here based on the definition of PV and PA, and all that's required to come up with the humidity ratio, which we came up with this 0.0255 mass of the vapor divided by the mass of the air. Okay, now the next thing we want to do is find dew point. And dew point now is the temperature at which condensation is going to start to occur in our airstream. And so that's the temperature we'd have to actually cool the mixture down to before we start condensing any water out of it. And so the dew point is found from the saturation temperature at a pressure of 3.94 kilopascals, because that's the actual pressure of the water vapor. So if we go back to the steam tables, I'm going to go ahead and put the steam tables back on here again, but we'll see that we're going to have to interpolate between them to make this thing work. Okay, so we found the dew point, and we are at a pressure of 3.94, and if you look up here at 3.94, you're going to see that we've got a 3.169 and a 4.246, and so this is going to be one of those little nasty interpolation problems. But you can see that the dew point temperature is going to lie between 25 degrees centigrade and 30 degrees centigrade, and you're going to have to linearly interpolate to find the value of the temperature corresponding to 3.94 kilopascals. And so I've done that. The two values that you're working in between at 25 degrees C. 25 degrees C, you've got a pressure of 3.169 kilopascals. 30 degrees C, you've got a pressure of 4.246 kilopascals. Our pressure is 3.94 kilopascals, so a linear interpolation between the 3.169 and 4.246 yields a temperature of 28.6 centigrade. So that's the dew point temperature. So if you had if you cool this mixture down to a temperature of 28.6 centigrade, then you'd start condensing some of the moisture out of it. So the dew point temperature then is 28.6 degrees centigrade. Okay. Now the next thing we're asked to find is the mass of the water vapor. And the mass of the water vapor we can find from the ideal gas law. From PV is equal to MRT. We can calculate the mass of the vapor then is equal to PV over RT. The pressure we're using, of course, though, is the pressure of the water vapor itself, and it's 3.494 kilopascals. The volume is the total volume that we're dealing with, 100 cubic meters. And then the R, of course, is the R for water vapor, which is 8.314 divided by the molecular weight. Water vapor H2O has a molecular weight of 18. So 8.314 divided by 18 gives us R for the water vapor, and we're at 35 centigrade, which is 308 Kelvin. So if we calculate this out using the ideal gas equations, PV is equal to MRT, we find out that 100 cubic meters of the air-water mixture has a mass of 2.77 kilograms. And so in this particular mixture, we have 2.77 kilograms of water vapor contained within this 100 cubic meters of an air-water mixture. Okay, the last thing we want to calculate is the mass of the air, and we can do mass of the air same way. We can either do mass of air is equal to P of the air, V is equal to mass of the air, RT. So we can calculate the mass of the air from the partial pressure of the air, of the dry air, or we could do it from the humidity ratio. So I just chose to take the humidity ratio here. Omega is equal to the mass of vapor divided by the mass of the air. So the mass of the air then is 2.77, which is what we just calculated here, divided by the humidity ratio, which is what we calculated up here earlier, of 0.255, and we find out that it's 108.6 kilograms. So in this particular mixture, we have 2.77 kilograms of moisture and 108.6 kilograms of air contained within this air-water mixture. And so working out by way of partial pressures, you've got to use the steam tables. You've got to find, you can find all the conditions that you want. The saturation temperature, the dew point temperature, the humidity ratio can be calculated after you find the pressures, and you can find the mass of the air from ideal gas conditions. You can find the mass of the water vapor from ideal gas conditions. And so you can work out the problem this way using partial pressures. And this is the way you'd have to work it if you didn't have one atmospheric pressure where you could use the psychometric charts. So let's take the same problem now and solve the problem using the psychometric chart and the psychometric relations. Some of the things are going to be very easy to find on the psychometric chart, and so this is the second part of the problem, and the psychometric relation. So let's just go straight, in this case, to the psychometric chart, and we'll put it back up here at the same point that we had before, and take a look at what we can get directly off the psych chart. In this particular case, we're looking at 35 degrees centigrade. So we're following at the dry bulb temperature. So we're following this line up at constant conditions till we get up to a relative humidity of 70%. So I got to keep on going till I get up here to 70%. And so this is this point right here. And so we're at 70% RH. The 70% constant RH is this curve that goes along here, and the dry bulb temperature of 35 degrees C is the temperature we're starting with here, 35, intersecting with 70% RH. So we have a very high moisture content. However, this is something that we can read directly off the chart. So one of the first things we want to find is the omega, and so that's just found from a horizontal line over. And so I didn't draw a very good horizontal line. Mine's kind of curved down, but anyway, if you read the horizontal line here, and I'll just make it real fat so that so that I can get the point at the right point here. But this horizontal line gives us the omega here, and that says that that's. I didn't read it quite as I think we got 255 before. I'm trying to give you what I actually got, and I got 25.4 grams. Went off. 25.4 grams. Divided per kilogram of air. So we end up with a situation here of about 25.4, which gives us omega is 0.0254 if we're talking about kilograms of water divided by kilogram of air. And so omega then is equal to that, but that's a direct lookup. Okay. The next thing we want to do is find the dew point. Dew point's a horizontal line. Dew point's a horizontal line that goes over from our point here, and so we can read that directly, and that comes out to be about 28.6 degrees centigrade. Just a direct line over here to the saturation gives us the dew point. And so the first two things that we have to calculate, the humidity ratio, omega, and the dew point, are direct lookups off of the psychometric chart. And so let me put my notes back on here, and we'll end up hopefully with the same numbers that we just picked off the psychometric chart, and that is omega is 25.4 grams of moisture per kilogram of dry air, which gives us omega of about 0.0254, which is very close to what we got last time. And then a horizontal line over to the saturation curve yields a dew point of 28.6 degrees centigrade. And so A and B come out real easy on the psych chart. It's a matter of a few seconds looking those things up. We've got to do some calculations to find the mass of the vapor and the mass of the air. But still, it's going to be a little bit faster to use the relationships off of the psychometric relations than it is to use the partial pressure data. Okay, so let's now find the C part. We want to find the mass of the vapor, and to do that we've got to find the partial pressure of the vapor, P sub V. So we've got an expression that says omega is equal to 0.622, that's on page 45 under psychometric relations. Omega is 0.622 times the pressure of the vapor over the pressure of the dry air, which is equal to 0.622 times the pressure of the vapor over the pressure of dry air. Of course, it's just the total pressure minus the pressure of the vapor. And so if we plug into this equation here for omega, we know that omega is 0.0254. We just found this out off the psych chart up here. So omega is 0.0254, that's 0.622 pressure of the vapor over the pressure that we've got is 100 kilopascals minus the pressure of the vapor. A little bit of algebra, but pressure of the vapor plus 0.0408 pressure of the vapor is 4.084, and so calculating out of these equations and using the 0.0254 number that I got, calculated pressure of vapor of 3.92 kilopascals. The other number that we got was 3.94 kilopascals, so we're pretty close. The difference is, I think this number was 0.0255 before, and it's 0.0254 was what I read off the psychometric chart. So we're pretty close. You calculate the mass of the vapor then from PV is equal to MRT, and you end up with the mass of the vapor is 2.7 kilograms. I think that's real close to, I think we got 2.72 kilograms before. And then if you use the humidity ratio, omega is the mass of vapor over the mass of air, then you calculate the mass of air to be about 108 kilograms. So it's obviously a little faster to work these problems out on the psychometric chart. If you get a psychometric problem, part of the scariest thing about the problem is the psychometric chart itself and all the various lines on the psychometric chart. But once you work with it and work out a few problems with it, I think you'll find that it's probably faster and easier for particularly a lot of these things that are direct lookups, such as omega and dew point and wet bulb and temperature, things like this that are direct lookups on the psych chart. It's really not all that hard to use. So this sort of concludes our discussion of the thermodynamics part of the review. We've covered first law, we've covered second law, ideal gas, 5 different cycles, psychometric relations, and partial pressure relations using the steam charts. And so I think this probably encompasses a good many of the types of problems and some good example problems typical of what you'd be seeing on the Fundamentals of Engineering exam, both in the morning and the afternoon sessions. Now, I want to finish up with a discussion of heat transfer, because this is part of this. Heat transfer is part of the specifications on the Fundamentals of Engineering exam under Thermodynamics. And so what you're going to be limited to, there's a fairly large section of heat transfer, though, in the supplied reference. And so what you should be aware of is that the heat transfer portion that you're responsible for on the Fundamentals exam for both for the morning and the afternoon, as far as the general exam is concerned, are really concerned with the concepts that are on page 53 and the top of page 54. About the first half of the column on page 54 is what you'll be responsible for. The rest of the heat transfer sections that are included there will be specifically for mechanical engineering students who are going to be taking the PM mechanical exam, and chemical engineering students who are going to be taking the PM chemical engineering exam. So if you're Chemi and ME and you're planning to take those exams in the afternoon, then you'll want to refer to the entire heat transfer section that's in the manual. However, if you're going to be concerned only with the general exam, then you're going to be responsible only for the heat transfer concepts that are on page 53 and the first column on page 54. So let's go over what you might, I think this is just a repeat of what I said. The heat transfer is part of thermo, and you're going to be limited to page 53 and 54. Now, the typical problems that you might encounter would be heat transfer through a composite wall or through a plane wall, through a cylinder, which would be comparable to a steam pipe carrying insulation that has insulation on the outside, and you want to know how much your heat losses are. There could be some problems on convective heat transfer. Just heat transfer is equal to heat transfer coefficient H times area times a temperature difference, delta T, or it could be radiation using the fourth power radiation law. So I've got 3 examples worked out that involve heat transfer through a plane wall, heat transfer through a composite wall, and heat transfer from a radiation heat source. So let's go through these 3 examples. The first one is heat transfer through a plane wall. Now this might be comparable, let's say, to a brick wall in a house. The thickness of the bricks are about 10 centimeters or roughly 4 inches thick. There's a certain thermal conductivity, and there are temperatures here that you're concerned with. Heat transfer occurs because of a temperature difference. If there's no temperature difference, there's not going to be heat transfer. And so if you calculate heat transfer, this is usually denoted by Q, and it is heat that is transferred through the wall as a result of a temperature difference. So in this particular case, we've got a 10 centimeter thick wall that has a thermal conductivity K of 1 watt per meter Kelvin, and we've got 2 temperature differences, T1 and T2, that are 25 degrees and 0 degrees respectively. So in this case, the direction of the heat transfer is from the high temperature to the low temperature, and so we've got the Fourier equation, or the conduction equation, on a per unit area basis. Q is just equal to K times delta T over L. And there's a negative sign in front of it because we're talking about heat transfer T2 minus T1. In this case, heat transfer, the direction of heat transfer is going to go from high temperature to low temperature, and our equation T2 minus T1 is the difference is going to be negative, so you have to stick a minus sign in front of it to make sure you have positive heat transfer that occurs in the direction of the temperature gradient, or dt dx. So in this particular case, we plug in 1 watt per meter degree Kelvin for the thermal conductivity K. The delta T is 0 minus 25, T2 minus T1. Length is 1/10 of a meter. And so you work this out and you've got 200 watts per square meter is the heat transfer through this plane wall with these two temperatures, T1 and T2, at 25 degrees C and 0 degrees C respectively. Now, if you wanted to get the total heat transfer, so in other words, if you wanted big Q, total heat transfer through that wall, then what you'd have to do is determine what the area of the wall is. Maybe the wall is 2.5 meters by 10 meters or something like this, so the wall might have an area of 25 square meters. And so you multiply the area, 25, times the heat transfer or the heat flux on a per unit area basis to get the total heat transfer through the wall. And that, of course, would be real important if you were doing analysis of your heat losses through a house or building or something like this. You'd have to calculate the heat losses through the wall, through the windows, and through the ceiling, and then calculate what your total heat load would be for air conditioning or for heating. And so this is an example of just a plain wall where you've got two different temperatures, you've got one material, and you're calculating the heat loss through that. Now, excuse me, another sneeze. Okay, let's put let's add some insulating material onto this wall. Example 17, page 32, which is the last page in the notes. We've got a plain wall. It has the same thickness and same material that we had before, 10 centimeters with thermal conductivity K1 of 1. But now we're going to add in some insulating material. We're just going to put a little equivalent to almost a 1-inch thick insulating board onto this plain wall. So this might be comparable to material that has a fairly good insulating capability of 0.05 watts per meter degree Kelvin. And so now the heat transfer that we have in this case, it's our same Q that's going through the system. The same Q that's going through the system now is heat transferred through an outside temperature again maintained at 0 degrees and an inside temperature of 25 degrees. And we've got 10 centimeter thick wall and a 2 centimeter thick surface. Now, the way that you consider the heat transfer or calculate heat transfer through a composite wall, as this would be called, is that you work this thing generally on the basis of sort of an electrical analogy. In the electrical analogy, Q corresponds to I in current in an electrical analogy. The driving potential in the case of an electrical diagram would be the voltage. That would be the driving potential. But in the case of heat transfer, the driving potential is temperature. And so you've got a temperature of 25 degrees C, which is the higher potential than 0 degrees C. So the heat transfer is going to occur in the direction of high temperature to low temperature. And then the resistances corresponding to the electrical resistances are thermal resistances, and the thermal resistances are equivalent to the length over the thermal conductivity. So L1 over K1 is the thermal resistance of the 10 centimeter material. L2 over K2 is the thermal resistance of the second 2 centimeter material, and that number is 0.1 over 1, same numbers we had a while ago, K over L, or L over K in this case. 0.1 over 1, and this one is 0.02 divided by 0.05. O2 is the length, and thermal conductivity of 0.05. So this turns out to be 0.1, this turns out to be 0.4, and so you sum these two resistances up, and this is 0.1 and this is 0.4. So you sum these two resistances up, and the total resistance turns out to be 0.5. And so delta T over the sum of the R's of 0.5 gives us the heat transfer. So that's 25 divided by 0.5, which is 50. Now, we had a situation a while ago where with just the 110 centimeter plane wall and a fairly high thermal conductivity of 1, we had 250 watts per square meter of heat that was being transferred through that plane wall. We add just 2 centimeters of an insulating material, in this case with 0.05 watts per meter Kelvin thermal conductivity, and that little 2 centimeter strip has 4 times as much insulating capability as the 10 centimeter strip that we had before. And so consequently, the heat transfer has been reduced from 250 watts per meter squared down to 50 watts per meter squared. And this is just a good example of the impact of insulation on a building, in that a small amount of insulation of very low thermal conductivity material can dramatically impact your heat loads in a building, which is why we insulate, to save energy. So this is an example of we worked one pure heat transfer problem just involving conduction with one plane wall, where we calculated using Fourier's law directly, minus Ka minus K dt over L, or dx. And then we used a composite wall where we had 2 resistances that we had and summed up those 2 thermal resistances to find the overall resistance to calculate Q. So this is the type of problem that you'll encounter on the FE exam when you're looking for heat transfer problems, generally plane walls involving thermal conductivities that could be composite or could be just a plain wall. The second type of exam problem that I'd like to illustrate for you is one involving radiation heat transfer. We're not going to do a convective heat transfer problem as such, because again, it's Q is equal to H times A times delta T, and it's a fairly straightforward calculation, so I didn't work out an example problem on that. The radiation heat transfer is a little bit more complicated, and it illustrates a couple of principles here that I'd like to show you, make sure that you're familiar with whenever you do these problems if you encounter them. So let's take the radiation heat transfer problem, and that is, we've got a cylindrical heat source, very small, 1 centimeter diameter by 10 centimeters long. So this could be a small heat source in a furnace. We're maintaining temperature at 700 degrees Kelvin, and in this particular case we're going to say we're going to allow this cylindrical heat source to exchange heat with surroundings at 300 degrees K, and we're going to make the assumption that this is black body radiation. So that means that's the most efficient radiation that we have, that there are no losses in the amount of energy that escapes the body. And so we've got an equation. The principal thing in dealing with radiation heat transfer is that you're working with 4th power of the absolute temperature. And so again, another admonition, make sure that you're converting your temperatures to absolute temperatures. In this particular case, I made it easy because I gave them in degrees Kelvin to start with. But the heat transfer by radiation then is equal to this equation in your reference manual on 53 or 54, I forgot which, but 4th power of the radiation, where Q is equal to the emissivity, epsilon, times the surface area, times the Stefan-Boltzmann constant, sigma, times T1 to the 4th minus T0 to the 4th. Now, if we're assuming black body radiation, the emissivity is 1, and so for a black body, that's going to be the assumption you're going to make for epsilon. And so the surface area is pi dl. So it's pi times the diameter of 0.01 meters times the length, which is 0.1 meters. So pi dl is pi times 0.01 times 0.1 times the Stefan-Boltzmann constant, and the Stefan-Boltzmann constant is one of those that's listed in your table of constants. It's also listed also in the heat transfer section, but it's 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth power. 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth power times the difference in temperatures to the fourth power. So that's 700 to the fourth minus 300 to the fourth. Real common mistake that you don't want to make is 700 minus 300 parentheses to the fourth power. That's wrong. It's each one to the fourth power. 700 raised to the fourth power minus 300 to the fourth power. And of course that's Kelvin to the fourth once you make those calculations. So Kelvin to the fourth here cancels with Kelvin to the fourth here. Meter squared here, dealing with surface area, cancels with meter squared here, and we're left with watts. So if you do this calculation, you come out, if I've done my math correctly, you end up with 41.3 watts, or about 41 watts of energy, of input energy would be, or power would be required to maintain the surface temperature of this cylinder at 700 degrees K, or 700 K, with the exchanging heat with the surroundings at 300 K. Well, this pretty much concludes the review of thermodynamics. I will put my phone number, fax, and email back up here again. And if you want to get in contact with me, my name is Dan Turner again, in the Mechanical Engineering Department at Texas A&M. And that's my phone number and my fax number and email. And if you have any questions after looking over this tape about the review session, or about thermodynamics, or about the fundamentals of engineering exam, I would be pleased to talk it over with you. So you can contact me. I hope that this will prove to be very helpful on the exam. I think it'll provide you a good idea of what's going to be covered on the FE exam in the thermodynamics area. And I wish you all much success in passing the fundamentals of engineering exam. Thank you.